A small dart of mass m is launched with an initial speed v at an angle of 30 degrees above the horizontal. At the moment it reaches the highest point in the path, it collides with and sticks to a wooden block of mass 5m that's suspended at the end of a string of negligible mass. The length from the ceiling to the center of mass is L. That causes the block to swing upward to a certain height h, making that angle theta with the vertical. Air resistance is negligible. In part A, we want to derive a formula for several different things, expressing all answers in terms of m, v, l, and any physical constants. So we first want to get the speed at which the dart strikes the block. Now, we cannot use conservation of energy here because we have no idea what this height is from the ground to where the block is, and we would have to know that in order to figure out this velocity, but we can just use properties of projectile motion because, if you remember, the formulas to break the initial velocity into components, the VOX, the initial horizontal velocity, is VO times the cosine of the angle, which in this case is 30 degrees, and the VOY, the initial vertical velocity, is VO times the sine of the angle, again 30 degrees. The initial velocity is V, and cosine of 30 is root 3 over 2. And for the vertical direction, it is going to be V times the sine of 30, which is 1/2, so we just end up getting V over 2. When the block reaches its highest point, it is traveling horizontally only because the vertical velocity has gone to 0, and since the horizontal velocity stays constant during the entire time, the highest point, it has this speed, the horizontal velocity. So that is your answer to part 1. For part 2, we want to figure out the horizontal distance that the block moves. And the horizontal distance, we're going to have to figure out also using stuff from projectile motion. We have to know how much time it's going to take. We know the velocity horizontally, but we need to know how much time it's going to take to move horizontally, and we can get the time by solving the vertical direction. So let's set up some projectile motion stuff. We have in the vertical direction, we know the initial velocity is that v over 2. We know the final velocity at the highest point in the vertical direction will be 0. The acceleration is equal to negative g, since we defined upward as the positive direction, and the time is the thing that connects the vertical with the horizontal. So we want to use the equation that has these 4 things in it and is missing the delta x or delta y, which is the first kinematics equation. V is equal to VO plus AT. Remember the 3-step process we go through for solving kinematics. First step is anything that's equal to 0, then set it equal to 0. So the final velocity is 0. Second step was to rearrange the equation without plugging the stuff in yet. So I'm going to bring the VO over to the left side and then divide both sides by A. And that will leave you with T is equal to negative VO over A. I'm plugging in the stuff from the list now. That's going to be negative V over 2 divided by A, which is negative G. The negative signs cancel out, and the 2 shifts down into the denominator. So we have a time of V over 2G. But remember, that's just how much time it takes. Now we have to look at the horizontal direction. So in the horizontal direction, the only equation you should be using horizontally is the constant velocity formula. V equals delta x over t, or in this case, we're going to use d, since that's what's given in the question. V equals d over t, and we're trying to solve this for d. So multiply both sides by t. So d is equal to v times t. The v in this equation is the horizontal velocity, which is this up here, the v times root 3 over 2, and the t is what we just solved for. So let's just multiply this formula by this formula. So that'll be root 3 over 2 v times v over 2g. We have two v's in the numerator, which multiply together. So that leaves you with a numerator of root 3 v squared. And then in the denominator, we have two 2's that multiply together. So we end up with a 4g in the denominator. And that is your answer for the total, the horizontal distance that the dart moves. Part 3. Now this question is different depending on whether you're in AP Physics 1 or AP Physics C. In AP Physics 1, it wants to know what is the maximum height that the block rises to. In AP Physics C, you have to go one step further and figure out what is that angle that the block swings up to. But for both classes, you have to start out the same way, which is by first figuring out what is the speed of the block immediately after the dart hits it. So that would be this V final right here, and that part comes from conservation of momentum, since the dart hitting the block is a collision. So we'll set up the conservation of momentum equation for a completely inelastic collision, or a perfectly inelastic collision. That is m1 v1 initial plus m2 v2 initial equals the combined mass m1 plus m2 times that combined velocity v final. M1 will represent the dart, M2 will represent the block, and initially the block is not moving, it is just hanging there, so that second momentum term goes to 0, and we can plug everything else in. M1, the mass of the dart, is just m, and its initial velocity right before the dart hits the block is that horizontal velocity, the v times root 3 over 2, and that's equal to, now on the other side, this combined mass is going to be m plus 5m, which is 6m, times that vf, which is what we're looking for. On both sides of the equation, we have an m, which cancels out, and divide both sides by 6. So that'll put a 6 in the denominator down here, and you end up getting vf is equal to root 3 over 12 times v. So that's just to get the speed of the block after the bullet hits it. Now we've got to do the second part of this, still on the same part, and that is that final velocity from conservation of momentum becomes the initial velocity for the conservation of energy as this block is swinging upward. So setting up a conservation of energy equation, Ki plus Ui equals Kf plus Uf. The block is initially moving. Remember, this is right after the dart has hit it, so that's caused the block to start moving. So it's going to be a 1/2 mv squared, where this is that v term in there. But this is the lowest point in the path of the block, so we're going to set that initial gravitational energy term to 0. And when it reaches the highest point up here, it momentarily stops right before it swings back down, so the kinetic energy at this point will be equal to 0. So plugging in the formulas, we have 1/2 times the mass, which is 6m, although that doesn't really matter since the whole thing's going to end up canceling out anyway, times the initial velocity squared, and again, that initial velocity squared comes from this final velocity, and that's equal to the gravitational energy, which is the mass 6m times g h final, which is just the h right here that we're looking for. We have a 6m on both sides, which we can cancel out, and we're trying to get h by itself, so let's just divide both sides by g. So h is equal to vi squared over 2g, and that vi, we've got to plug in this formula. So when we square everything in that formula, root 3 squared is 3, then you have a v squared divided by 12 squared, which is 144, and then we still have this 2g in the bottom. The 3 in the numerator will cancel out with the 144 in the denominator. 144 divided by 3 is 48. So this simplifies to 1 over 48. and 48 times 2 is 96. So the final thing you end up with for the height is equal to v squared over 96g. If you're in AP Physics 1, that's your answer, and you can skip ahead about 30 to 40 seconds probably. If you're in AP Physics C, the one final step is to get the angle, and to do that is something similar to what we've done before, where we go back to the diagram, we draw this horizontal line to create a right triangle, and this part of the triangle, that side, is going to be the total length of the string minus that bottom part, which is h. So I can say that this is L minus h. This side of the triangle over here is the length, and I can get the angle now from using an inverse cosine of the adjacent side, L minus h, over the hypotenuse, which is L, and then you just have to plug this formula for h into that right there. So there was a lot with that part, but the next part is very short. The period of the resulting oscillations, and this is actually the first part of this problem that actually has to do with this chapter and not a previous chapter. So we know the formula for the period of oscillations of a pendulum is 2 pi times the square root of L over G. And notice that this formula already has everything in it that we need. It's in terms of an L, and everything else in there is a constant, the pi and the G, and doesn't depend on the velocity or the mass or anything else. So this formula works for part 4. That is the period of the resulting oscillations. Moving on to part B. So in a second experiment, you have a dart with more mass being launched at the same angle, same speed and angle, and it too collides with the same wooden block. So we want to indicate whether the following quantities are greater than, less than, or the same as those that we determined in part A. For the first part of part B, this question is once again different for AP Physics 1 versus AP Physics C. That's comparing either the maximum height that the block rises or the maximum angle the block achieves, which if the block achieves a bigger height, it's obviously going to be at a bigger angle. So they are kind of interrelated. So if you look back at this formula, you see that final velocity. So it looks like it doesn't depend on the mass, but don't be fooled by that, because you still needed to put you would still need to put a new mass in over here and right here if M1 was bigger, and that would ultimately end up making this number a little bit smaller, so that when you divide by that number, this fraction is now bigger. So the final velocity is bigger, and that should just kind of make intuitive sense. If you have a much more massive dart that hits this thing, because it's transferring more momentum, it's going to cause this V final to be larger. And since that V final is larger, that means the H is going to be bigger, and also the theta. So everything basically gets increased. It's greater than what it was in part A because of the increase in the velocity after the collision. And then for part 2, what is the period of the resulting oscillations? How does that compare? Well, we're going to end up using the same formula, and because it just depends on the length, which didn't change, and the G, which didn't change, nothing changes about the oscillations themselves when you use a bigger dart. It's just going to swing to a slightly larger angle, but the actual time period it takes to go back and forth as a pendulum will be exactly the same as it was in part A.